Okay, it's time to get started. Last time we talked about double integrals in polar coordinates and applications of double integrals in physics problems. So when we have an integral in double integral in polar coordinates, we need to set up the measure of integration, which goes like, so which goes as r dr times d theta. So in other words, if you have an integral in Cartesian coordinates, the differential, the infinitesimal unit of area, dx times dy, should be replaced by r times dr times d theta. So the reason why you can thinking in terms of dimensional perspectives, we know that theta is dimensionless, right? It's a number between 0 and 2 pi, whereas r has units of distance, right? So area is measured in units of distance squared. Therefore, in order to have the dimensions right, you need to multiply dr d theta by something of dimension length, which in this case should be equal to r. So yeah, so often these dimensional considerations are useful to check the answer for sanity and see if it's correct. So we did that, and we did some applications. I want to mention maybe one more application, and for the rest you can read in the book or elsewhere. Is the moment of inertia. Right, so physically, a moment of inertia is the analog of a mass. So what moment of inertia is for rotational motion is what mass is for the proper motion, right? So there's a famous F equals ma formula for the motion of point particles, right? When a is the acceleration, so its analog for rotation would look like, maybe somebody can tell me. So what's the analog of F equals ma for rotation? Some of you must have taken. Yeah, so tau equals I times alpha, that's right. So here, tau is the torque, right? We talked about it when we discussed bicycle, how to pedal optimally on the bicycle, right? So tau is equal to I times, and then, so Alex has to denote alpha, and alpha is the angular acceleration, right? So it's the second time derivative of theta, right? So and then, well, let's write it in terms of a scalar function, and its direction is pointed towards upwards, right? So if angle theta changes like this, right, then the rate of change, right? So the angular velocity it is directed upwards. We can call it omega. So this is and then the derivative of omega itself is the angular acceleration, which is called alpha, right? So I is called the moment of inertia. Alpha is angular acceleration. And tau is torque, which is a cross product of radius vector times the force. So yes, and another way to write it, so as we know that the second Newton's law can also be written as the derivative of the momentum over time. And here we can write tau as the derivative of the angular momentum over time. So where angular momentum is the product of the moment of inertia times the angular velocity. So there's a complete analogy between the proper motion and the rotational motion. So if you have the simplest example, you have a point particle moving on a circle of radius r, and now let's treat it as there's a point particle m, which moves with the velocity v over a circle of radius r. So here its moment of inertia is equal to m times r squared, right? And then let's just check that this the formula works, right? So write tau is equal to m. So we know that and the torque, yeah. So the force here. So then, if you think of it as a if you think of this mass as a attached on a string, right, and then you're rotating the string around, then there's a tension force of the string that acts on this mass, right? So therefore, the force is directed towards the center. So in this case, torque is equal to 0. So it rotates, you know, at a constant speed. But then the moment of inertia is mr squared, right? What did I want to write? Oh yeah, right. So I just wanted to show the analogy between this equation and this equation. So, and now let's say that the force is changing, right? So that you are applying some force to it, which changes in direction. Then you would have, you know, r cross f on the left, and is equal to I it is equal to I times okay, never mind. So do yes, it's equal to I times alpha, right? Or it's equal to m times, well, we should use small r here. Yeah, so okay, I'm going to start with the next line here. So now let's switch to the projection on the z-axis. Right? So we know that the direction of the torque and direction of the angular acceleration is goes upwards. Right? So with torque and acceleration, they look out of the page. So we can use it as scalar quantities. So r times f times possibly sine of the angle between them. And on the right hand side, so it's essentially it's an effective force that is applied, right? Like with the bike, with the bike problem, we had certain effective torque, which was parallel to the axis of rotation of the gear. And then here we have you have m r squared times the angular acceleration, right, which is alpha. Now, what alpha is, right? So alpha is equal to second derivative of theta over time, and we know that if the particle makes an angle theta, then this distance is equal to the arc length is equal to r times theta. So therefore, if you multiply both parts by r, you have r alpha is equal to r d2 theta over dt squared. Right, so the derivative is linear, so you can write it as d s, right, over dt squared, where s is the arc length, which is the acceleration, the linear acceleration. So therefore, this is equal to r. right? And one of the r's you can cancel. So from this equation, you have the force. There's some effective force is equal to ma. And so it shows that these two equations are equivalent, provided that the moment of inertia of a point particle, which spins around an axis r with distance r apart, is equal to mr squared. Okay, but now since we can integrate, we can have a generalization of that of this. So we can have some oddly shaped body like that with a certain density function. So you were still talking about planar story. So then there's axis of rotation going somewhere here, and it all happens in a plane like that. So it can rotate like this. So then the moment of inertia of that body would be assigned axis of rotation. Question R cross F we did to find force based on the empirical fact acceleration is always tangential. No, so the see here, look at the picture. So R times R cross F is the torque, right? So if the force is always central, then there is no torque, right? And then the particle is moving at a constant speed. Now, if force happens to be non-tangential, like that, but still it lies inside the circle. Well, excuse me, inside the plane. Then the torque would still be perpendicular to the plane, right? And its magnitude will be equal to r times f times sine alpha, where alpha is that angle. Then if you're wondering where is the acceleration goes, well, I mean, here, of course, acceleration will go in the same way as the force, right? So it will go along this purple vector. So here, no, acceleration, in fact, if your point particle moves along the circle with a constant speed, the tangential acceleration is zero, right? It only has the normal component. So it was just to illustrate this. The moment of inertia is really just the analog of the mass for the rotational motion. Other questions? Okay, so now say you have this shape in the plane, and then you want to rotate that, right? So coming back to our pizza analogy from yesterday, so you're cooking a pizza, and then you're spinning this disc, right, around the axis. And yes, I want to find what's the energy, or what is the momentum of inertia of this thing. So what you would do, you would break this body into small pieces, each of them having mass dm, located at a distance r. So then the contribution to the moment of inertia from that particular mass is equal to dm times r squared, right? But now let's assume that this function rho of xy describes the density profile in the shape. So therefore, we can write dm as rho, well, at that point, right? So at xy times dv, where dv is the unit volume, or well, area, should I say. So somehow I always area, right? Times r squared. And then in order to find the total moment of inertia, we need to integrate the di over the area of the body of the shape, which brings us to the formula, right? This brings us to the integral of r squared rho dA, the area. And so that's the moment of inertia. Yes. So r squared is the same as x squared plus y squared. Okay. So let's do this pizza example, right? So let's find the, so you have a disk. This is going to show integration of polar coordinates, right? So say we have a disk. With constant density, right? So the density is equal to some function. So rho of xy is equal to just constant rho, right? And the radius of the disk is equal to r. And sort of the disk is thin. So what's the moment of inertia relative to the axis, which goes through the center of the disk, and which is perpendicular to the plane of the disk. So moment of inertia is equal to this integral, right, of rho times r squared dA over the whole disk. And of course here it's much better to use polar coordinates because it's symmetric. So we would integrate integral from 0 to 2 pi d theta, integral from 0 to capital R. And then remember we need to add another power of R from the measure. So we'll maybe either tomorrow or Friday, we'll talk in general how to make change of variables in multiple integrals. And this R, this factor R between the Cartesian measure and the polar measure will be called the Jacobian of that transformation. So you can write what happens under the general change of coordinates. But anyhow, here the answer will be equal to, so integral factorize this, right? So you can take 2 pi rho r to the 4th over 4, right? Which is equal to yeah, so it's equal to pi rho r to the 4 divided by 2, right? And now let's express it in terms of, so that's the answer in terms of mass and the density. But now let's compare it against the point mass m, which is separated at a distance r. So what is the mass of the disk, right? So mass is equal to the density times the area, surface area, which is pi r squared. So we can rewrite this formula like this, right? So it's 1/2 pi rho r squared times r squared, right? And so it's equal to, and this thing is the mass. So that gives you 1/2 mass r squared, right? Which means that if you take there's a coefficient 1/2. So so in other words, if you have a point particle m at a distance r, and you want to rotate that, it feels twice heavier, so to say, than the same mass if it would be distributed uniformly over the disk, right? And if you try to rotate this around the center. Any questions? Okay. Good. So Luther is so much more concise than 7a. 7a, the example from the book, physics 7a. Oh, I see. Yeah, I think part of the problem with those early physics classes, if you say take them in school, like or this AP or whatever, is that they are, so it's so much easier to formulate those things using calculus method than without them. So if you do those things without calculus, it's really sometimes very confusing. Maybe that was part of the problem. Okay. And then probably also for physics, you know that there's a theorem about shifting the axis of rotation, right? So then you have, so you have a rod like this, and then there's an axis of rotation, so it goes to the center. Does anybody remember the answer for this case? In this case, what's the I for the rod of length L? This is big L, mass M. Remember what I is equal to? Yeah, that's right. It's 1/12, right? Yeah, so it's 1/12 of ml squared. And then there's the, yes, what's the parallel axis theorem? That's what Alex is saying. And then you can, if you shift the axis of rotation by some distance, let's say distance d, right, then the I changes, right? So I becomes I plus md squared. Right, but you have to be careful here because, you know, for example, you should not do, you should not treat this formula literally, right? So it should be used, it should be understood as follows. So if you have first axis goes through the center of mass, let's say this is I star is the thing for the center of mass, and then if you do the shift, right, so then you add md squared. So of course you should not do it. You should not put it from here to back to the end and then back. So you can imagine shifting the axis left and right, and then every time you add md squared, which is of course wrong. We can, yeah, this theorem you can easily prove again using the calculation. Okay. Okay, so I think in the interest of time, we'll skip the rest of 15.3, but probability and expectation value. Maybe just mention what expectation value is. So, you know, there's a notion of a distribution function. So say f of xy is a, what in probability people call a probability distribution. Right, so it's a function that, so say you have a random process which sort of changes continuously, and the you want to determine a probability of some event from some event happening, right? And then it can be described by some function. So it can be discrete function, it can be continuous function, right? So say here is the one of the examples of this probability distribution is, for example, e to the minus x squared over 2 sigma, right? So that's the so-called normal probability distribution that appears in many examples. And then you want to calculate what will be the value of some observable, some quantity in probability, right? So you have a function. So say there is the observable is described by some function phi of xy, right? And then you can ask yourself, what is the average? What is the value of this quantity on average, right? So then here goes the average or expectation value, which is the integral, well, double or triple or whatever. So I'm just going to write it in general. So there's an integral over, well, the domain where this function is defined, right? So phi of xy times f of xy dx dy, and then you divide it by integral over f of xy dx dy itself, right? So and typically this function is picked. We pick this function in such a way that that integral in the denominator is equal to 1, right? So therefore, it's simply the answer is simply equal to the numerator, right? So you integrate the probability distribution function with the function that describes your observable, and that calculates you the expectation value. Right, so for example, in quantum mechanics, and so for those of you who go to physics classes, so you know there's this there are quantum observables, for example, operator of coordinate operator of momentum, which is minus I h bar d over dx, right? It's a linear operator that acts on some Hilbert space, and then you can calculate the average value, say, of some function of x and p, right? By it will be some integral, well, usually some three-dimensional integral over three-dimensional space, right? If multiplied by the, so this operator phi, right, acting on the wave function, which is denoted with letters. The quantum mechanics, right, is the probability distribution. So here at that point, and so you take the shape of the wave function in say in the atom, like say in hydrogen atom, right? You'll find it at so you can, well, you want to solve Schrödinger equation, and then it will tell you exactly where, at which distance from the center, what is the probability to find an electron. Yeah, and then if you want to calculate what is the expected expectation value of the momentum or coordinate of any other operator, then you need to do this calculation. Yes. Do we center probability distribution at the origin? We don't have to. Sometimes it's there, sometimes it's not. Here I just gave an example. Right, so for example, probability of, let's say, say you are looking at the distribution of heights of trees, right, of some species like palm trees, right? Of course, the probability center will not be at the origin; it will be at some average height of those trees, and then it will have some bell-shaped curve like that. Right, so another example from classical physics is the distribution of velocities of molecules in the air. Right, so there's the average velocity, or there's average squared velocity, and so on. And in that case, again, the center of the probability distribution is not at the center; rather, it's at some positive value. No, we cannot have negative probability. No, like that. That's not physical yet. Also, the fact that this integral, so here it's actually because, well, phi is actually the amplitude, right? So we need to multiply by psi conjugate here. So psi is the amplitude of probability. In quantum mechanics, which is in sense the square root. So it's a complex function, right? And then the probability itself is the absolute value of psi, right? So that's the probability. So sometimes in quantum mechanics, we write expectation value like this. There's this operator phi, and then you write in terms of this Bryan-Cat notation. So that will be the average, so it's the expectation value of operator phi over the state psi, meaning that we're calculating expectation value given the probability distribution absolute value psi fx squared. So the fact that this integral here is equal to 1, so you would need to divide it by this integral over psi of x squared d3x over the whole volume. And the fact that this thing is equal to 1 reflects the fact that sum of all probabilities is equal to 1, right? So if you toss a coin, it can be either one of the two possibilities. So the total probability is 100%. It's either heads or tails. In, say, continuous probability theory, you have a continuum of outcomes, but you need to integrate them with weight, which is this probability function. And it should be normalized to 1. And so this fact is in quantum mechanics is related to the unitarity of quantum mechanics. That's the whole, yeah. Okay. Questions? I skipped a question. What are the chapters in scope for the quiz? So for the quiz, we'll have it will be for the previous week. So it's the minima and maxima and Lagrange multipliers, and maybe there'll be something about partial derivatives in the beginning. But yeah, so it's mostly on this 15, what is it? 14.7, 14.8, right? No, we'll do 15 next week. There's a lot of material. It's better to let it sink in. Okay, so moving on, in chapter 15, we are at 15.5, which is the surface area. So the task is to find the area of the surface given by equation z is equal to f of xy, provided that xy live in some set D as a subset of R2. So you can have, again, here's the coordinate space. And the surface behaves like this. So say, for simplicity, assume that D is a rectangle. And if you pick a small square inside this rectangle, its image on the curve would look like, on the surface, excuse me, it would look like this, right? Some curved rectangle. So our task first is to calculate this infinitesimal small area, right? And then integrate over the whole set D in order to find the full area, right? So clearly the area here is just the delta x, delta y. But now what happens if we tilt it, right? So now I'm going to magnify a little bit the same color. That's the small plaquette dx delta x delta y. And then the part of the surface might look like this. So if we zoom in close enough, right, it would look like a parallelogram. Like this, right? So it's a parallelogram that is built on two vectors. The one goes along the x-axis, so it's obtained by intersecting the surface with a plane that is perpendicular to the x-axis and with a plane which is perpendicular to the y-axis. So if we call this vector A and that vector B, then as we know from previous work, that so maybe we'll use a different letter here not to confuse it with the area downstairs, right? So let's call it delta. We'll make it infinitesimal later, and this is delta A. And here's the delta T. So according to our theory, delta T is equal to the absolute value of the cross product of A and B. And so because that's the area of this parallelogram here. And then what we need to do to complete the calculation is to express vectors A and B in terms of the data of the curve of the surface and do the integral over D. So closed inspection tells us that vector A, it has only components in x-axis and in z-axis. So x goes here, y goes there, and z goes over here. So vector A would have components delta x times I plus, well, let's write it like the vector, right? So it's equal to delta x comma 0, and here it will be the partial derivative of fx. At this point, right? So let's just call this point x, xy. In fact, we should label it, right? Because we want to sum. Let's put it xi, yi. And here it's also labeled xi, yi. Right? Because that's what it is. Like it's vector A is tangent to the surface, and therefore it's tangent to the curve that lies in that plane. And similarly, vector B has components delta y, f prime y, at xi, yi. And here, sort of, well, again, we're assuming that we're making a partition as before. We are partitioning this domain here, this area, into both horizontally and vertically, right? And then we have, yi plus 1, and then we have here xi plus 1. And in fact, we should label delta x's as well. So delta xi is equal to xi plus 1 minus xi. Delta yi is yi plus 1 minus yi. Okay, now let's calculate the cross product. Then if you're really pedantic to put indices everywhere. So ai cos bi is equal to the determinant of the matrix ijk delta x 0 fx. I'm going to suppress some indices. 0 delta yi fy. Now we open up the thing. So for I, we'll have minus fx delta y. For j, we'll have minus fy delta x. Right, and for k, we'll have delta xi times delta yi. These are the components of the vector. I think I forgot something. Yeah, I'm sorry. It's not just the derivative; it also multiplies the deltas, right? So it's still delta x, but multiplied by f prime multiplied by delta xi, right? So it's the if you have a function like this, right? So this function f of x, and then if this is delta x, then that is delta, like the vertical distance is delta x times f prime x, right? F prime is just the tangent of the angle. So we need to multiply by delta x, and here we need to multiply by delta y. No, I look something's wrong here. So delta x here, delta y here. That's why it will be all these guys, and then we can single it out. So we can take out delta a. So delta a we denote it with delta x times delta y, and perhaps even with the minus sign, no, without the minus. And then it will have components negative fx, negative fy, and 1. Okay, that's the vector. We know that the area should thought of as something with the direction. And finally, the absolute value of that, ai cross bi, the square root of 1 plus fx squared plus y squared. Delta a I, put I here. And finally, we need to take the limit and integrate. So that we need to take we'll compose the Riemann sum, right? So we are calculating Riemann sum over all I and all j from the respective partitions, ai cross bi. Actually, I think so I have to correct a bunch of things, right? So the Yeah. Anyway, so let me not label. And then by sending the delta x to 0 and delta y to 0, let's put it this way, we'll get that the area is equal to integral over d square root of 1 plus fx squared plus fy squared dx dy. That's the formula. So notice the similarity between that formula and this formula and that of the length of the curve, right? So in the length of the curve, we had the square root 1 plus derivative squared, and then there was only one function. But now we have two functions. We also integrated, it is also a two-dimensional integral instead of one-dimensional. So let's do an example. So let's find the area of the paraboloid, surface area of the paraboloid. Z is equal to x squared plus y squared that lies under plane z equals 10. So z is less or equal than 10 and greater or equal than 0. So then here we have a paraboloid like that, right? So we need to figure out which set we need to integrate in xy plane. So it will be a disk of radius square root 10. So we'll set up the integral with this disk d, square root of 1 plus, and then the derivatives z prime x is equal to 2x, the z prime y is equal to 2y. It's 1 plus 4 x squared plus 4 y squared dx dy. And of course, it's easy to switch to polar coordinates. So we'll do integral from its symmetric d theta 0 to 2 pi, then integral from 0 to square root 10, 1 plus 4r squared r. Remember that extra r we need to put r dr, which gives us 2 pi multiplied by the integral from 1 plus 4u du. Rather, let's do it in a smarter way. So we'll make a change of variables here. We'll just say that this u is equal to 1 plus 4r squared, and then du is equal to 8r dr. Right, so when u is equal to 0, so when r is equal to 0, u is equal to 1. When r is equal to square root 10, u is equal to 41. So the integral will go from 1 to 41, u to the 1/2 du, 1/8. Right? So it's pi over 4 times u to the 3/2 divided by 3/2 between 1 and 41, which is whatever it is, right? It's equal to pi over 6, right, times 41 to the power 3/2 minus 1. Yeah. Take it to make it. Yeah. Yeah, that's right. So I denoted u the quadratic expression. Okay. Yeah, that's the example. Okay, let's take a quick break, and then after we'll come back from the break, we'll talk about triple integrals. Yeah. Okay, let's continue. Has anybody did the research on pizza prices? So what will be the price for an infinite pizza if you continue the trend of the prices? I think Shiloh wanted to do that, right? So do we know how to bankrupt a pizza joint already? Ask them to make an infinite pizza. Yeah, sure. So just plot on the graph all the pick your favorite pizza place, right? And then plot all the prices and against the radius of the disk, and then try to approximate it with some function. And then if this function is polynomial, then we're in trouble because the infinite pizza will be infinitely expensive. But if it's a log function or something like that, well, log is also bad. But if it's something else, then maybe it's okay. Okay, so then let's go to triple integrals. And in fact, try to stop on 3, so n integrals. So the idea is to construct again the Riemann sum. So let me give you the answer in terms of construction for triple integrals. So we take a parallelepiped. It's the simplest set over which to integrate, and then we tessellate it, right? So we cut it, slice it into smaller parallelepipeds. Like that, and then we select one of them somewhere here or in the middle, right? And it looks like a parallelepiped with sides delta x, delta y, and delta z. So now we need to take partition of in all directions. So we need the product of 3 partitions, px, py, and pz. And then there will be the volume, the delta v I j k, labeled by three indices, delta xi times delta yj times delta zk, where I, j, and k they vary in, well, so they belong to this partition. Let's call it partition P. And so they belong to this partition set, which simply tells us where and how we cut the parallelepiped into this smaller parallelepipeds. And then we compose the triple Riemann sum. Yeah, before we do so, and say there's a function of 3 variables, which is, for simplicity, let's say it's continuous. It's f of x, y, z, and say this is parallelepiped B. Where x, y, z belongs in B, which is continuous. So just for concreteness, let's say B is the product of segments AB, CD, and EF. Right? And then the Riemann sum would be, again, it doesn't matter where we pick the point, where in each of the functions integrable, we can pick a point anywhere in the inside each of those small parallelepipeds, and then multiplied by the small volume. So it will be sum of xi yj zk times delta v ijk. And so we construct this gadget. So yeah, just for computers, we can put some stars here, meaning that the point where we evaluate the function does not have to belong in a corner. Rather, it can be anywhere in this parallelepiped here. So that has coordinates x star, y star, j, and z star. Okay. Okay, and then as we send the, so if the limit exists, right, so then we define the triple integral over b of f of x, y, z dv as the limit of this Riemann sum, as the mesh of the partition P goes to 0. In fact, mesh should probably say that meshes of all the partitions should go to 0. So it's mesh of px, px, py, and pz goes to 0. So if the limit exists, then this defines as the triple integral. And you can see how to generalize it to n integral. So in fact, let's consider Bn, the n-dimensional hyperparallelepiped, right? We just made this up. So it's the product of A1, A1B1 times A2B2. Right? It's the Cartesian product. We're welcome to do any number of these products times Bn. So we take partitions P1, P2, and so on, Pn. We construct this big Riemann sum, which is sum of all indices I1 through In, and then have a function of n variables, x1 star, xn star, multiplied by delta x1 times delta x I1. I need to have a double index, delta x I1, etc., delta x In. And then as you take the limit, as all meshes of those partitions, pi goes to 0 for all I, that gives you the, well, I'm going to do it only once. You don't have to write this like that. You can just write one integral. So integral of this, f of x1 through xn, and then you can write it like this. You can write it as dnx. So this is a shorthand for the differential, dx1 through dxn. And in the future, you can just write it as a single integral, right? From the context, it's clear it's clear how many integrations you actually need to do. Dnx. Right, so that's the n-dimensional Riemann integral. So when it comes to calculations, we need to represent these integrals iteratively, right? So we'll integrate out one variable first, then the other, then another, until we'll get to the last one, which will be just a ordinary definite integral. Right, so there's an analog of Fubini theorem here. For triple integrals. Which says that, or in the, so the integral over b of xyz dv, right, it's equal to, it's integral from a to b dx, from c to d dy, from e to f dz. It's I'm using the same notations as we had above, f of x, y, z. Right, so here B is this parallelepiped, right, the box. However, well, as you can imagine, if examples become, so it doesn't have to be like this, right? So in future, you want to learn how to integrate over any shape, right, with sort of some 3D shape that is bounded by some surfaces. Then, of course, those limits, integration limits over here will also depend on coordinates. And in fact, not since it's a triple integral or for quadruple or etc., those functions will be of more than one coordinate typically. Okay. So let's look at an example. Say we have a function bounded by, we have a solid which is bounded between two different surfaces. Right, so there's one cap here, the surface, and then there's another surface on the bottom. Like this, and they form a solid here. So let's say this surface is given by equation z equals u2 of xy. This one is given by equation u1 of xy, and then in between, yeah, so let's call there's this space S for solid, right? And S is the set of all coordinates in three-dimensional space, provided that x and y, they live in some set D. You can think of it as so that is, is all some plane, and then there's a set D here, right, where all x and y live. And that Z is bounded between u1 of xy, which is unknown surfaces, and u2 of xy. right? So, and then there's a function f that is defined on S. It's a function that takes S to R, right? It's a continuous real valued function that lives on S. So our task is to integrate this function f over the solid S. How do we do that? Well, the so the idea is to do the z integral first, right? Because we know that z is bounded. So remember we had a discussion about what's the way to do the iterated integrals for the double integral, and then we picked the direction of slicing. So here the direction of slicing is also is important to choose. So we would pick it like this, right? We would go into vertical direction. So we would integrate over this long cylinders or parallelepipeds, depending on what we're doing. So we would integrate over those patches. There's some patch of area dA here, or rather at the bottom, right? That's what we call dt in the previous story. And then here, we have some patch of area dA, which is dx dy. So here so in other words, we can write it like this. We can do we can integrate over dA after we've done the integral over z. Right. So after the z integral is done, we have a function of two variables, x and y, and that's the example that we already know. It's the double integral over the area. So yeah. So that's kind of the general formula, and then there's a simplification of that. Sort of if the following thing is true. So if it happens that the projection onto the xy axis is sort of a simple shape, right? So we can write it as well, I guess I need to. I think I can change it over here. Right, so if this d is of a specific form, that is d itself, right, is bounded by two graphs, right? So we can say here, for example, that the shape d itself is bounded between two graphs, x equals, say, h2 of y, or from here, and then from here, x equals h1 of y, and y is bounded, say, it's between this line and that line. So we have y is equal to, excuse me, yeah, so y is equal to c and y is equal to d. So in other words, it may happen that we can write a more explicit formula. So that already refers to taking a double integral, right? So if s is built in such a way that it's set of all x, y, and z in R3 such that y varies between c and d, x varies between h1 of y and h2 of y, and finally z goes between u1 and u2 of x, y. well, then you can explicitly do the double integral as well. And in this case, the triple integral over the volume will be equal to this nested integral. So integral from C to D dy, integral from h1 of y to h2 of y dx, integral from u1 of xy to u2 of xy dz, f of x, y, z. And alternatively, you can do this double integral if you have the set D in xy plane, which is bounded in a different direction. So it can be bounded by graphs y equals some function of x, and the y equals to h1 of x and y equals to h2 of x, and x is bounded between two numbers. Then you would just do the similar calculation of the double integral. But anyhow, so let's do an example. Otherwise, it's getting sort of the way we formulate it abstractly is maybe a bit confusing. Of course, once you do several examples, you'd see what's going on. Of course, in triple integrals, it's even more important to get stuff right from the beginning. So you would do the calculation so that the calculation would be mostly economic. Okay. So let's do an example. So first, let's take the simple one. Let's say we have a tetrahedron or other face of the tetrahedron here, which with coordinates (1, 0, 0, 0, 1, 0, 0, 0, 1). So want to integrate. So yeah, so let's say, and it's the tetrahedron is bounded by this plane here. We know what the equation of this plane is. It's the x plus y plus z equals 1. So it's bounded by this plane and planes x equals 0, y equals 0, z equals 0. Right, so it's a tetrahedron like the which is excised by this four planes. It belongs entirely to the first quadrant. So let's call this tetrahedron T, and we want to find an integral of function say, z over T. So that's the integral I that we want to calculate. Okay. So let's see what's going on here. The projection on xy axis looks quite simple. Right, it looks like this triangle here. It's 0.10, 0, 1, 0, 0. So we can integrate. So let's call this set D. So D here is given by set of x, y inside R2 such that x is between 0 and 1 and y is between, so this line is what? It's x plus y equals 1, and y there is between 1 minus x and 0. Right, so therefore, according to our formula, we can write the integral I as the nested integral. So integral over x goes last. Then we would integrate vertically in this direction here, and then in the first iterated integral will be integral in z direction, right? So z here is equal to 1 minus x minus y. So z is bounded by, so we can therefore say that T is a set of, well, x, vector x in R3, such that, well, xy belong to D. We describe what D is, and Z changes between 0 and 1 minus x minus y. So therefore, the integral will go like that. From y goes from 0 to 1 minus x. And then z integral over z goes from 0 to 1 minus x minus y. Then the function z dz. Okay. So we have set up the integral according to the last rule. And yeah, let's calculate it. So the inner integral will be equal to, so this thing equals z squared half between 0 and 1 minus x minus y. So we do dy times that thing squared, right? So it's 1 minus x minus y squared. Now let's do this integral. We can denote u to be equal 1 minus x, sorry. Yeah, so if u is 1 minus x minus y, then du is equal to minus, dy is equal to minus du. And then when y is equal to 0, u is equal to 1 minus x. And when y is equal to 1 minus x, u is equal to 0. Right, so that gives us integral from 0 to 1 dx, integral from 1 minus x to 0 minus du, u squared. I forgot factor 1/2, yes, 1/2 here. So this can be written as 1/2 integral from 0 to 1 dx, integral from 0 to 1 minus x u squared du, which in turn equals 1/3, right? So we could put 1/6, 0 to 1 dx, 1 minus x cubed. Yes, and then that's equal to 1/6 minus 1/4, 1 minus x to the 4, right between 0 and 1, which is equal to 1/24. Yeah. So let me not go right now over all types of integrals. I think it's better to leave for discussion or for the homework. So you may have different kinds of geometries, right? You can have, so we discussed, well, two types now when you have a kind of bounded, this shape is bounded in all three directions, and then we can sort of consecutively take out integral one by one. You can also have something when the, well, it clearly it can happen in any direction, right? It can happen in direction z, x, y, or it can go into, like, you know, any line, right? So, or it can be some of some irregular shape. So every time you're going to have to be creative. So I leave you with all this fun exercises. So encourage you to do them as soon as possible. We'll do some, yeah. So there's still some time to do them before the discussion. We'll, if you have some trouble doing them, we can discuss them on Friday. Okay. So I think instead, let's talk about something conceptually new, which is the spherical and cylindrical coordinates. Yeah, so as you can see, it's a meticulous work which does not forgive any errors. You have to be very diligent and make sure that you're very careful in all the calculations. So next we go to 15.7, which is cylindrical coordinates. Well, let me do them at once. 15.7 and 15.8, cylindrical and spherical. So as the name suggests, cylindrical coordinates work like this. We have to, so it's the, when your problem has a certain cylindrical symmetry, then it's it makes sense to switch to, so these two systems are three-dimensional generalizations of polar coordinates. And then, so cylindrical coordinates work like this. If you have a point with coordinates x, y, and z in Cartesian coordinate system, then you do the following. So first, you take the plane, which is parallel to the xy axis and that pass through this point, and then you connect it with the z-axis. So that will be radius r, right? And then you would use the same polar, and then you will treat this plane as the polar plane. Well, unfortunately, the way I drew this point is a bit, the polar angle will be small. So you have a polar axis, polar angle theta, right? And then so this point will have coordinates r cosine theta 0 z. Well, I think I need to make a better picture. Let's try something different. Instead, let me project down to the polar axis, to the plane. Okay, so that's the Cartesian set of coordinates x, y, and z. And then say you have a point somewhere here. Right, so first you project it down onto the xy coordinate, xy plane. At this point we have coordinates x, y, 0. And then you treat this point using the polar coordinates in the xy plane. So you would have a polar angle, polar angle theta. So that here this point will be x 0, 0. This point is 0, y 0. Right, and then here you can just find this z projection. 0, 0, z. So the change of variable goes like this, right? So z does not change, and then you just say that x is equal to r times cosine theta, y is equal to r times sine theta, and z is equal to z. So z does not change. So that's how to go from Cartesian into cylindrical. Okay, so let's calculate an integral in those, and then yeah, so how the calculation of the triple integral will go. So if we have a triple integral in the Cartesian coordinates, dx, dy, dz, then since dz does not change, the only things that change are this dx, dy part, this polar part. So therefore, after change of variables, this becomes triple integral of f of r cosine theta, r sine theta z, right, times r dr d theta dz. So it's as simple as that. It will be slightly more complicated for spherical coordinates. Probably we'll talk about spherical coordinates tomorrow. But okay, so let's do an example here. So say we do we have this integral. Yeah, so so you have let's say there's a solid S, which is bounded by the following thing. So it's cylinder x squared plus y squared is equal to 1. And then it's bounded by plane z is equal to 4. And it's bounded by paraboloid. Z equals to 1 minus x squared minus y squared. So it looks like this. We have a cylinder, and then it's capped from below by a paraboloid like this. So this is this paraboloid. Well, it does look like like a like some water bottles, wine bottles, whatever. Or maybe I think the closest that I know to this shape is the storage for tennis balls. Like they're sold in a store with this kind of tube, plastic tube, so it's flat from the top, right? And it's sort of concave inside from the bottom. And so you can fit 3 or 4 tennis balls in there. So this plane is z equals to 4. This is the cylinder. And this is the paraboloid. And let's just integrate the constant function, right? So say there's density rho, which is constant. So we want to find the mass of this thing. So mass will be this triple integral over S of function rho d volume, right? So rho is a constant, we can take it out. And now put the axis, symmetry axis, that will be the polar or cylindrical axis of symmetry. And so clearly it's convenient to switch to cylindrical coordinate here because that's what that's the most convenient thing to do. We want to start the integral over z, right? We want to integrate it from. So since it's cylindrically symmetric, we know that the outer integral will be over theta, which will factorize. It will simply give us the multiple of 2 pi, right? So and then we want to integrate over so then there will be integral over r, right, over the radius. We'll put the limits there, and then the first integral we do will be integral over z, and it's integral of well, of 1, right, of the constant from 1 minus this x minus y squared, which is 1 minus r squared. Actually, we forgot r. So there will be r from the change of variables, an integral from 1 minus r squared to 4, right? And in r, there will be integral from 0 to 1, right? Okay, does everybody agree? So yeah, let's execute the integral. Right, so it's equal to rho times 2 pi, integral from 0 to 1 r dr, integral from 1 minus r squared to 4 dz, which is just this difference. Right, so it will be going down a bit. So that gives us what? That gives us 2 pi rho integral r dr times 4 minus 1 plus r squared. So it will be 3r plus 3r cubed dr. Right, and yeah, so that's equal to 2 pi rho times 3/2 r squared plus 1/4 r to the 4th. From 0 to 1, which gives us 2 pi rho times 3/2 plus 1/4. So that's 5/4. It's 5/2 pi rho. Yeah, so that will be the mass of the cylinder with this half sphere. Well, it's not exactly half sphere with this paraboloid thing removed. Yeah, this is how this works. Any questions? So yes, like the best way to practice this is to master, or the best way to master this is to practice. So there are a bunch of practice problems and homework. Go ahead and do them. And 7/2 pi rho. So it's 3/2 plus 2 plus. Yeah, thank you. That's right. 7. Yeah, I did. Yeah, 7. Yeah, thank you. I added the 2 fractions incorrectly. Yes. Correct. We're gonna get 7/4 times 2. Yes, thank you. Yeah, good. Yeah, it's always better to check on the way. Yeah, so you can read in the book. The book has a bunch of examples. You can do the homework, and we'll discuss those on Friday. So tomorrow we'll have a quiz in the second, starting from the second hour as usual. The quiz will cover the content of the previous week, and during the first hour I can talk a bit more. Maybe we'll talk about spherical coordinates during the first hour, and on Friday I'll speak a bit about change of variables and Jacobians, and then we'll do a discussion and a Q&A session. Okay. Great. Thanks for joining. I'll see you guys tomorrow. Thanks. Bye.